Higher Notes 1.1, Motion Equations and Graphs. In part 3, we're going to look at how the gradient of some of the motion graphs and the area under the line can be physically significant. So let's begin with a displacement time graph. Displacement on the y-axis, of course, and time on the x-axis. Well, if we had a typical uniform acceleration type displacement curve like that, and we chose a certain instant in time, say here, well, at that instant, if we were to draw a tangent to the curve like that tangent would have a gradient Now, you know how to get the gradient of a straight line. It's the change in the y-coordinate divided by the change in the x-coordinate. So, in maths, you would call it delta y over delta x. But in this particular case, our delta y-coordinate is the change in displacement, so it's really a displacement, and the change in the x-coordinate is a measure of time. So what we find then is that the gradient of the tangent at that point, in other words, the gradient of the ST graph at a point in time is basically equal to delta y over delta x, which in this case is s over t, which of course is v, velocity. So the gradient of an ST graph, a displacement time graph, gives us the velocity of the body at that point in time. Notice, of course, that if we go to a later time, the gradient has got steeper, so there'd be a greater velocity. If we were to go to an earlier point in time, the gradient is less steep, so there would be a lower velocity. And that's consistent with the fact that this represents, remember, a uniform acceleration. Let's do the same thing, but this time with a velocity time graph. Again, all motions are for uniform accelerations. So let's get our axes drawn. Might want to put a little line under that bit. So this is going to be our velocity time graph. Always, of course, put in the origin. Not too worried about the values on the axis, on either axis, just concerned at the moment with the shape and the gradient. So it's uniform acceleration we're dealing with, of course, in all of these examples. So we have our line going up in a nice straight way. That's a uniform acceleration. So that's the velocity time graph. And of course, because this is a straight line, getting the gradient is very straightforward. It's as before, change in the y coordinate divided by the change in the x coordinate. There we are. So mathematically, you could think of this as your change in y, and down here we have our change in x to that point. But of course the change in the y coordinate is actually the final velocity minus the initial velocity, which is v minus u. And the change in the x coordinate is essentially the time take away 0. In other words, it's just the time taken for the change to occur. So when we get the gradient then of this graph, and it is a constant gradient, so this is a VT graph, well, it equals the change in y over the change in x. That's what you'd say in maths. But in this case, that's v minus u divided by t, which I hope you recognize is the acceleration of the body. So taking the gradient of a velocity time graph gives us the acceleration of the body, and that of course is a constant because all of our concerns here are with a uniform acceleration, and so that is constant. Okay, so that's the first thing on that graph. Now there's something else we can do with this graph though. We can look at the area under the graph. So if I sort of shade in the area under the graph, like so. Well, you'll know what I'm getting at here from your National 5 work. For a VT graph, we can always say that the area under the graph, well, it's going to be half the base times the height. And if you look at what the base is, that's a half of t times v. Now you can think of that as being a half of v times t. Now half of v, which is the halfway point between 0 and the maximum velocity, the final velocity, that actually is just v bar. That's like u plus v over 2. So the halfway point of the velocity is the average velocity v bar. So what we're basically saying down here is that that is just v bar times t. And of course we know that the average velocity times the time is the displacement. So the area under the graph equals the displacement if it's a velocity time graph. If it were a speed time graph, it would be the distance. So just be on the lookout for whether it's velocity or speed. And finally, you already know that the acceleration time graph, what that looks like. Let's just draw a little line there. disappeared. There he is. Okay, so just for completeness, we'll sketch the acceleration time graph again. Now, of course, this is for a uniform acceleration. So as you know, this graph will always be a nice straight line. These construction lines are always good to draw in just to show at what particular time the motion stops. Okay, we're not, obviously the gradient of this graph is 0 because it's flat, so there's no great significance to that gradient. There's nothing to be learned from the area under that graph. We just need to know what it looks like. Just going back up to the displacement time graph, you'll notice we look at the gradient of that graph, but the area under that graph is of no significance to us. But for the velocity time graph, the gradient and the area are significant. So that is how we can usefully use the gradient and the area under the graph. Just a couple of final observations. This is on some velocity time graph observations. Probably obvious to you, but worth making anyway. Now that you know the gradient of a velocity time graph gives you the acceleration, hopefully you would be happy agreeing that, say we had an acceleration like that, that would be a particular acceleration. Here is a different acceleration, so different motion. The red line is less steep, so it's got a smaller gradient. So smaller gradient, which means smaller acceleration. Whereas this one has a larger gradient, which means a larger acceleration. Okay, and finally, in this part, similar sort of thing on velocity time graph again. Time on the x-axis, velocity on the y. So say you had a particular body. I'm just going to set this ruler to 20 degrees. So say you had that acceleration starting at that particular initial velocity, and another body were to start at a higher velocity but increase its speed at that rate, and yet another one were to do that. Well, all three of those bodies begin at different initial velocities and they end up at different final velocities. But the one feature they all have in common, all of these lines have the same gradient so represent the same acceleration. They're all parallel. So different lines on a velocity time graph which are parallel have the same gradient, and therefore they represent the same acceleration. And that brings us to an end of this particular note.